Physics 20. So what we're going to do is we're going to go into an introduction of physics here before we get into lesson one. What I'd like everybody to do is go through and do this introduction, just the reading part. It's on paradigm shifts and how our perception changes over time. So how we constantly change what we think is normal. So you will go ahead and do this puzzle. So try to connect 9 dots using only 4 straight lines without lifting your pen. So yeah, go ahead and do that. The key for that's on the next page. I'm going to see if I can skip it. Yeah, I skipped it. So this is where you guys will read to. And then when you're done that, we're going to get into some physics basics here. So some of this stuff are things that you've done already. Some of it you've maybe never seen before. The first thing is uncertainties of measurement. You might have never seen this before. Maybe you did. If you have, that's great. So first thing, we've got 2 different types here. We've got something called accuracy in physics, and we've got precision. So accuracy, what that's talking about is how far off of the predicted value were you? And what I mean by that is, let's say that you knew that acceleration due to gravity is 9.81 meters per second squared. We'll talk more about the units and stuff if you forget that later. But let's say you knew that, right? You knew it from your textbooks. You knew it because other people have done experiments. That's the predicted value you should get. But let's say that you did an experiment. So that's, the experimental value in our equation. So you did an experiment and you got 9.79 meters per second squared. So that's what we're talking about, how far off of you. And what we're going to be able to do is put your answer and compare it to the predicted answer. We can get a percent error out of that, and that's what this equation is down here. And all you do for that is you'd put in your experimental value here. So that's going to be your 9.71 meters per second squared. That's your experiment, right? You'd subtract the predicted value, which is 9.81, and then divide it by the predicted value. And what these lines on the side mean, that's absolute values, right? So if you get a negative answer in here, you just make it a positive. Just take the positive of that and then multiply by 100. That gives you your percent error. I'll give you guys a chance to do some of these questions at the end of this lesson. So, okay, so that's accuracy, how far off you are from the actual predicted value. Now, precision. So precision is limited to the finest division on its scale. And what I mean by that, let's see if I can turn the camera around. Yeah, okay. Oh. Okay, so if we look at our scale here, you can see on, I gotta get myself figured out here. Oh, that's weird. Okay, so I've got millimeters on this top one, right? And you can see if I zoom in there, well, it's harder than you think. You should try that. Okay, so I've got each tick here represents a millimeter. So a millimeter is going to be my precision in this case. I can't go like, down to like 0.2 of a millimeter because I just can't be really sure about that. So the precision doesn't really follow through. But let's say if I looked at the other side, this bottom scale here is going up by centimeters. And it looks like I've got, 1 and then 1.5. So my precision on that one would be just 0.5 because other than that, I can't really be that sure about anywhere in between the ticks. So that's what we mean by precision. So if you're looking at, for this example, it says a student measures the mass of a ball 4 times and gets 1.238, 1.241, 1.2 yada yada yada. So if you add these 4 numbers up and then divide by 4 to figure out the average between them, you get this as a number. And then what this next part means is plus or minus 0.002. That means that I'm uncertain about that measurement within 0.002. And the way I got that is I know that, okay, so 1.239, that's my average between those 4 numbers. But then if I take the biggest number here, so let's say 1.241, and subtract that number, I get this, right? So there's that much left in that, if that makes sense. Hopefully that did. Okay, so moving on. So when adding and subtracting measurements, round to the same precision or to your least precise value. So all that really means is if you look at your decimals, so if I added up these three numbers, then you can see that 12.6 is my least precise, right? Whatever scale I was using, this scale was or less precise than this one, and less precise even than this one. My answer can only be as precise as my worst value or my least precise value. So if you added all these three numbers up, you'd get something like this, with 8.12 on your scale, if that's what it was, right? Showing that you're like really precise there. But then what you have to do is go back to your least precise value. So just one decimal place there because 12.6 was the least precise. All right. So looking at significant digits now. Says significant digits are all of the certain digits from a measurement plus one uncertain estimated digit. What I mean by that is if we were able to like measure this green thing I've drawn up here, and our scale was the one we have above, I'd say this was 2, and then I'd say 2.8, right? I'm kind of estimating at that point. So it'd be 2.8. And in this case, I would say I have two significant digits. So for all non-logarithmic values, so that just means like not like the pH scale and that goes up by factors of 10, regardless of any decimal position, any of the digits 1 to 9 is a significant digit. 0 may be significant. So we've got 3 significant digits in all of these, right? You just don't count the 0 to the left, let's say in this case. You don't count that 0. So we've just got these 3 here. You count these 3 on the end. So what it's really saying, like when it says 0.0023, and then they chose to put another 0 there. Whoever wrote this number down, they chose to put that 0 there because they're saying, I'm that sure that that 0 belongs there. They wouldn't have put it there at all if they were uncertain about it. So it's significant. Same with this one, right? So 2.3, and then they chose to write a 0. They're saying that that 0 matters. That they're that precise in their measurement. And then 2.03, yeah, that's 3 as well. Okay, number 2, leading zeros are not significant. So kind of what I was saying here. So that 0 is not significant. These 2 are not significant. It's just the trailing ones that are significant. So this case as well, there would be 3 significant digits. There would be 5 significant digits in that case. There would be 5 significant digits in that case as well. Okay, so we're not going to do much with the logarithmic one, but for logarithmic values such as the pH scale, any digit to the left of the decimal is not significant. So like the 1 here is not significant. You'd say this has 2 significant digits. A pH of 7 has no significant digits. Yeah, it's kind of a nice to know, but we won't really be using it too much in this course. All right, so when manipulating data, and what I mean by manipulating is like adding or multiplying or subtracting, any operation that you do. So when adding or subtracting, we're going to treat it a little bit different than we are going to treat multiplying and dividing. So adding and subtracting, we take our least precise value. So in this case, that's 12.3, right? That was the least precise number that I had. And then my answer, like if you add these all together, I get 12.76. And then what I would have to do is just round my answer to 24.8 because I can only be as accurate as my least precise value. So that's adding and subtracting. Dividing is a little bit different. All we do for dividing, and to tell you the truth, in Physics 20, this is going to be the situation almost 90% of the time because we're almost always going to be adding or subtracting in our calculations. So if that's the case, all you do is look at the number with the least significant digits. So this one has 3 significant digits. This number had 5 significant digits. Now I just know that whatever my answer might come out to be, I need to round my answer to be the lowest significant digit. So it needs to have 3 as well. So all you do is go through the question, keep all of your, actually that's what it says here. So number 3. So what you would do if you were going to make this calculation is you go through and keep all of your significant digits, like just keep all the numbers that you possibly can, and then do the calculation that way, making sure your order of operations is correct. And then you get this, number with way too many digits on the end, right? We're not going to have that many for our final answer. All you end up doing, though, is just rounding this number down to that. So see that this number I got here is different than this number I got here if you rounded your numbers throughout. In this case, they both would have rounded to 22.1, but you could see that if this number was a little bit bigger, it would have rounded up to 22.2, and that could be the difference between a right and wrong answer for a numerical response on a P8 or a diploma. And again, just where I got the rounding it to 3 significant digits is because if I look back up to my original question, my lowest one has 3 significant digits in it. All right. Okay, so last thing for significant digits here is that if you're doing a calculation, though, that involves exact numbers, something like, 12 eggs, you can't have 12.2 eggs, or you could, but that wouldn't make much sense in this case. If you're doing like whole numbers like that, you just don't include that in your lowest significant digits, right? So if I had 12 eggs times 52.3 grams per egg, so actually, I'm looking at this right now. If you had 12 eggs times 52.3 grams per egg, if you look at this number, the 52.3, it has 3 significant digits. So this should also have 3 significant digits. So this is wrong. This should say 628 grams because this is now 3 significant digits. This one as well. So I look at the precision of this number. There's 4 significant digits there. My answer should also only have 4 significant digits. So this would be 160.3 grams is what my answer should be there. I was just testing you to see if that was right now. So this last part here is just rounding. So just to make sure that you guys are clear on rounding, I probably should have had this at the beginning. If you had a number like 1.2345 rounded to 3 digits, if I look at 4, right, it's 4 or lower, so that would round down to just 2.3. If the number is 5 or higher afterward, then this would round up to a 3, so 12.3. Okay, so I'm going to end that video there, and I'm going to carry on with scientific notation in the next video. So I'll see you guys in that video.